thing, could you turn in your extra credit assignment? All right, if you got your extra credit, turn it in. Just stand down front. Thank you. How many?
I just got
everybody's. Thank you. All right. Next thing we need to take care of. Thank you. Next thing is the exam date, and so would anybody suggest the date? I'd like to get at least two. Friday what?
14th. Yeah.
October 14th?
Yeah.
Oh, okay. Any others?
Friday.
What?
Controls is 9.
Hold it, what's another date? Anybody? I mean, does anybody want it? All right, I'll tell you what, we'll just do it this way. How many people want it Friday, October 14th? Unanimous, all right. That's it. That's the exam date, okay? All right, so it's not this Friday, it's after we get back to it. Okay, I'm fine with that, and by the way, it doesn't matter to me. I just try to accommodate people because I know I've had cases in my life, right, like 3 exams in one day. That can be a little tedious. But that's neither here nor there. Now, questions about the homework. You had, I think I gave you 2 problems in ours of book, 2 or 3. Right? And I didn't cover the inductor, but which? So anybody, you got a question for me? I'd like to do at least one of them. Yes. The second one. All right. Can you give me? It's a plot, right?
Yep.
Just say that. You know, here, don't worry about it. This. Correct me if I'm wrong. This is F, right? Frequency. And is it flat and go down like this?
Yep.
Oh, it's this. Hold on. This is different. Like that?
Yeah, but it does have a flat portion.
Right here? Okay. All right. Now, what's this frequency?
100 kilohertz.
And this?
1 meg.
What's the height here?
100 ohms.
Now, it really should be the log of 100 ohms, but he's saying that's the value there. And this?
It just says the absolute value received. Oh, it doesn't give that. But it tells you that it's...
No, this is 20 dB, right?
That's right.
And this is minus 20? Alright, what does it ask for again?
It asks for an equivalent circuit to represent this impedance.
Alright, just taking a look at this, what is that likely to be? Now, I didn't cover that one. It's an inductor, right? At very low frequencies, the wire's resistance will cause it to have a constant value. Then when you go over that, an inductor has an impedance of J omega L. You know, follow it? That's going to bring it up to 20 dB per decade. This is the self-resonant frequency right there. That's when you basically have the maximum value. You have a capacitor in parallel with an inductor at resonance, so that means you're going to have, it should be, if there was no resistance, it would be infinite. Then it's going to fall down to 20 dB per decade. That's what it amounts to. Now, if you're doing this, you all remember Bode plots, right? When you have them in signals and systems, how many do? When you do Bode plots, you talk about poles, you talk about zeros, right? Anytime you do a function like this is the magnitude of z, this. I'll put it over here. Z itself, right here. Well, when I look at this, always start off, it has some constant value, k. We don't know what that value is. Now, here's where the important parts are. At this frequency, it's called a pole, it starts going up at, sorry, this is gonna be a 0, it's gonna start going up at 20 dB per decade, y'all follow? So I'm just gonna do this, yeah?
There is another plot right beneath it.
Yeah, it's a phase plot. The phase is gonna flip, it's gonna go from plus 90 to minus 90 at the resonance, I think. Okay. Alright. Just tells you if it's plus 90, it's an inductive reactance, if it's minus 90, it's a capacitive reactance that dominates. That's the only thing that phase plot does. So then, I take a look at this, and it comes in at 100 kilohertz. So that means I have S plus some A, that's gonna be the lower frequency there where it comes in at. Then, here is the self-resonance, and that's gonna be a double pole. It's gonna be S plus B squared. Now, I'll get to this in a second, but y'all remember doing these things at least vaguely from your signals and systems course. Y'all remember that? Now, S itself, in our case, is just J omega. That's all. So when we do this, normally I start at this point. I come here and I say this is K, and this is going to be J omega plus A, and then I have over J omega plus B squared, and I'm just putting in the values. Then after that, what I do, and this is the way, I think it's the best way to do it. What I try to do is get this imaginary term plus 1. This imaginary term, that imaginary term plus 1. So in other words, here's what happens. And you'll see why in a second. I'm going to factor out, or I'm going to do this. So I'm going to divide by A and multiply by A. So this becomes A times K over J omega divided by A plus 1. Then down here, I've got to divide by B, and since that's going to be I'm going to have a B squared coming out here, and I'll have 1 plus J omega over B squared. The only thing I've done there is I'm trying to get these things to look like something where I have 1 plus some J number. Do y'all follow me in this class? Now, the reason I'm doing that is because when I go ahead and I take 20, this is just Z in general, when I take 20 times the log of this, you'll see it really clearly. When I take 20 times the log of the magnitude of Z, that's going to be 20 times the log here of this term AK over B squared. Then it's going to be plus 20 times the log of simply the magnitude of 1 plus J omega over A. Then it's going to be minus, and this is going to be 20 times the log of the magnitude of really 1 plus J omega over B, but this is squared, so I have to put squared. Now, the only thing I've done there is now I'm putting it in terms of a Bode plot form. Y'all follow me? We're going to talk about the poles and zeros in a second. I'm going to do one thing right off the bat at the end here. When you have the log of anything to a power, you can just take that power out in front. Y'all follow me, class? So I can make this minus 40. And leave it like that. Now, when you're at low frequencies, take it omega equals 0. Hear me now. When omega is equal to 0, this is what? The log of 1. What is the log of 1? 0. Y'all follow me? So if omega is 0, start at the lowest possible frequency. This term has no effect. When omega is equal to 0 here, but it's still log of 1, it's 0 as well. Do y'all follow me? So at very low frequencies, the only thing that happens is this, right there. Okay? Now we're going to equate that in a second to 100 ohms. But hear me out in the whole thing. With me? Now the next thing is, you have to realize what we do with this number. That is the first 0 that starts the thing ramping up. It's at 100 kilohertz. That tells me that this value of A here will be 2 pi times 100 kilohertz, because that's where we want the thing to become of the order. If you look at this with that. when you're at that resonant, or at 100 kilohertz to pi times 100 kilohertz, this thing right here will become a value of 1. You'll have J1 plus 1, or magnitude square root of 2, and that's where these things cut in and out. Follow me, everyone? So we come over here and we can say that A over there is going to be 2 pi times 100 megahertz, or just times 10 to the 5th. Now what about B? What's B going to be? You all remember this, don't you, class? I mean, this is not news to you, right? Just a refresher course. That's at 1 megahertz, right? So now we take B is equal to 2 pi, right? Times 10 to the 6th. Y'all follow me? And that will actually, when we get these values, that will work. That will be the representation. We can go and put it in this form. I think he uses a P, doesn't he? Not an S? Maybe I'm wrong. Doesn't he have a form with an S plus something or not? I don't know. Or P plus something. Well, we'll see in a second. Okay, so now I've got the value for A and B. Now I need the value of K. So I take a look at this. I have 20 times the log of Z, and this is going to be down here, so 20 times the log of 100, or 10 squared, is equal to, and here I can have 20 times the log of A over B squared, and plus 20 times the log of K. That's what we need. So if you look at this, the log of 10 squared is what? Well, the log of 10 is 1, the log of 10 squared is 2, correct, class? Times 20 is 40, right? Then I'm going to take this, and I'll subtract that off, so it's 20 times the log here of the magnitude of A, and that's 2 pi times 10 to the 5th, over B, which is 2 pi times 10 to the 6th. But this one is squared, and this will be equal to 20 times the log of K, or, so what's this one going to be? Can somebody just give me this value on the side? I'm trying to show you how I would do this problem. There may be an alternative way of doing it, but this should make sense. And this is approximate. So the log of, well, what is that going to be? You're going to have, so that's going to be 10 to the minus 7th over 2 pi, 20 times the log of, I don't know. Anyone? I'm glad you asked that. It's a good thought. You're not used to doing this. Huh?
I got, it's like 195.69.
We're just going to leave it there. Now look, that's equal to 20, right? Times log of K. So we can get K by taking whatever this is, 195.6 divided by 20, take it to the power 10. So that's going to be 195.6 over 20. The power 10 would be K, and you can tell me what that is.
6.28 times 10 to the 9.
6.28 times what?
10 to the 9.
Times 10 to the 9, is that right? Let's see. 19, 20, that's 10. Yeah, that sounds about right. That sounds right. Okay, that's K, and then, I mean, I'm assuming we didn't blow anything here. I think this should be about right. Go ahead.
I did a different way, got the same answer, so.
Okay, well that's good enough. Now, after that, the only thing we do is take these values and plug them in here. So K is that value, and I'm putting in this form of S. That's the usual way to do these. They can do them with J omega or with some other variable, but typically it's with S. It's commonly done. So here, I'll just, what is it? That's 6.28 times 10 to the 9. 10 to the 9 here. And then it's gonna be S plus A, and A is, 5 times 10 to the 5th. And down here, B is 5 times 10 to the 6th. Alright, is that what he has as in the solutions? The answers aren't there. I know there are. How many tried this one? Okay. Nobody. Okay. What?
What do you say the inductance and?
No, I mean, this is the actual form of the actual, it's the Bode plot form. All right, what are you asking for?
So the problem wanted just a circuit with an inductor.
All right, this is the actual Bode of that. This would be something that replicates that plot as a Bode plot. So if you want the values, here's where I'm gonna go back now. I didn't complete the inductor model. Remember last time I did the capacitor and the resistor. For an inductor, if you have an inductor in cell, at low frequencies, an inductor looks like an inductor. Makes sense. The impedance of this would be J makes L. But there's one thing you can't get away from is that there's an inherent amount of resistance to the wire. I mean, even at DC, you're going to have some, it may be very small, but some. In our case, it's 100 ohms. So this is 100 ohms right there. Now, when you look at this, there's also going to be in parallel with that a capacitance. And this is a parasitic capacitance. The reason we model, and this is the way the whole circuit looks, if I come over here and here, this would be what the actual circuit element would look like as an impedance model, as a, I should say, a model that's typically accepted for in the frequency domain. The reason you're going to have that is because anytime you drive current through here, you're going to develop a voltage, and anytime there's a voltage difference between 2 points, there's inherently some charge difference, and that means there's a capacitance that's used to represent that effect. Y'all follow me, class? Now, at low frequencies, at very low frequencies, this looks just like a resistor, 100 ohms. As you move up in frequency, all of a sudden, these two things become a factor, and you get a pole. All right, you actually get something where this inductor starts driving up the impedance. Finally, when you get it at a high enough frequency, this capacitor kicks in and starts shorting out everything. So if you look at this cut frequency right here, just look at the impedance of these two things. If you have 100 plus J omega L as just the impedance of the top part, this would be the low frequency value. All right. When omega L is equal to 100, that's where that all of a sudden the J omega effect starts taking over. Do y'all follow me on this, class? Right. The way it'll always be when the imaginary component is equal to the real component, at that frequency is when the pole or zero really kicks in. For this one, you can see if omega L is equal to 100, right? Then that means L is equal to 100 over omega, and omega is 2 pi times 10 to the 5th, right? Isn't that, this is this low frequency kick in, right? Y'all follow me, class? So what's that value gonna be? Anybody give that to me? Yes. You're gonna need to know that, so it's just as well I did. 100 over 10 to the 5th, that's 10 to the minus 3 over 2 pi. So it's something of the order of what?
It's 1.6 times 10 to the negative 4.
All right. 1.6 times 10 to the minus 4 henries. All right. And then, is that jive with the answer?
No.
For L?
It's got a 1 nano henry inductor.
That's 100 kilograms, right? And this is 1 megahertz, right? Right? What?
Actually, the problem.
Yeah, well, hold on, before you do, I'm checking something here. Alright, this frequency is a self-resonance, so if we think about this, F self-resonance is equal to 1 over 2 pi square root of LC, right? That's gotta be right. If that's L, and this is 10 to the 5th, or 10 to the 6th here, right? Then I go ahead and I'll take 2 pi times that, and then 1 over that, so I have 1 over 2 pi times 10 to the 6th here, and that's equal to square root of LC. So I take that and square it, that's equal to LC. If I divide this by L, I get C. So, just for kicks, do this for me. Take that value of L, we calculate, and what do you get for this?
That L value? 1.6 to the negative 10.
Farads? What does the book have for that?
1 microfarad.
1 micro.
Yes.
Something like this. Mine is a different circuit layout than theirs. I put the capacitor in parallel with the series combination, what he did, and he can get the same thing, basically. What he did is this. He took this, right here, and he's using this to get that. Now, it will get it, if you look at this, and it's gonna do the same thing, it's just the capacitor now is just over the 100 ohms. That's not a true inductor. I mean, inductive capacitance is across the entire thing, if you look at the model for it. So for this one, you could get it, and if you look at this, then, if you're gonna use that, this is one model, the model I had would work too, but if you look at this, right here, and this is gonna be J omega L, and this is gonna be 1 over J omega C. So for this, the impedance is going to be equal to J omega L, right? And then it's going to be plus 1 over R, 1 over 100 plus J omega C here. And when you take that, let's see, I'm going to multiply by 100 top and bottom here. That's going to be 1, and this is going to be times 100, and this is going to be times 100. And then, if I do it that way, this is going to be the pole that actually turns on, I believe, first. And so, if I said 1 is equal to omega times RC, or 100, times C right here. And I want the value for C, it's going to be 1 over 100, omega is 2 pi, and when that turns on is 100 kilohertz, so it's times 10 to the 5th. you get for this value of C here? Doesn't look bad. Anybody? What did you get?
0.6 times 10 minus 8 micro.
Now, what's the answer?
It was microfarad.
It says one on there.
1 microfarad for the capacitor.
That's right.
And what does this come out to be?
0.6 times 10 to the minus.
For what?
1.6 times 10 to the minus.
It's all by 2 prime. Yeah, the 2 prime is on some real one. So this one is not using 2 pi at all.
Oh, let me just do something. I'm gonna do, if this is 1 over SC, and this is S times L, let's just do this right. So my Zn, Z of S here will be equal to SL plus, and I'm just gonna leave this as R for now. R, right here. So it's gonna be plus 1 over R plus SC. Then I'm gonna go ahead and I'll say this is gonna be SL plus R over 1 plus SRC here. Then I need a common denominator. So I have SL times 1 plus SRC. It's gonna be that plus R all over 1 plus SRC here. It's gonna be equal to my Z here. Then multiply this out. So then I have, it's going to be S squared times RC. I'll put it right here. So that's going to be S squared LRC. And then it's going to be plus SL. Then it's going to be plus R over 1 plus SRC. And then first I divide, I come out with value of R in front here. So get rid of R there. Plus 1. And after that, divide by L. And then divide by C. Alright. So that means this is the hole back there. And that means this is where this hole is kicking in at. Yeah, it has to be that one. I'm sorry. This would make sense. Then you're gonna have, when S is equal to this frequency here, or it's gonna be 2 pi times 10 to the 5th over R L, that should be 1, and that means L is this divided by 100, and that ain't right either, is it? Because that's gonna be.
Still has a 2 pi factor in it.
Huh?
Our results don't have pi terms in them at all, there's just 1 times some magnitude, so.
Are these frequencies in hertz, or are they in?
It says hertz.
Let me get back, let me do this, I'll tell you, I don't wanna take up any more class time with this, but the way, the typical way you model something like this frequency first cut for this, if you're doing a standard inductor model, and I might as well just go over this right now and show you where it is in the book. I think there's something very, either that's wrong in the answers or something that I'm missing. This one. Because just for kicks, all right, I want to check one thing. See if this resonant frequency based on their things agrees with 1 megahertz. The resonant frequency is going to be equal to 1 over 2 pi square root of LC. That's going to be true. So if you take a look at this, he has 1 over 2 pi square root, and his value of L was
1 nano.
1 nano, 10 to the minus 9. So it's 10 to the minus 9 times, what's the value of C?
1 micro.
10 to the minus 6. So that's 1 over 2 pi, and that's square root of 10 to the minus 15. That I don't know. So what is that? Is that 1 meg? All right, the answer in the book is wrong on that one. This has to be true. That has to be, this frequency right here has to agree with this frequency. You follow me? It has to be 1 megahertz. It's not. There's something wrong with that answer, and I'll check that one. But I'm sorry. And it may be part of the errata for that book, but I didn't check into it. Now let me go through, and I'll just show you the proper model for an inductor. And I want to do it here. And I want to tell you where it is in Whitmer's book. And then we have 2 things to do there. Sorry I spent so much time in that one, but it was a little irritating. The book that's from his name is Clayton Hall. He's very famous in EMC. Usually his answers are right, but that one can't be. So, when we're talking about EMC stuff, and we're in chapter 9. We did the resistor, we did the capacitor. So the model he has for the equivalent inductor is on page 511 at the bottom. And what it amounts to is this. You're always going to start with an inductor. That's the value. It's got to have some inherent resistance of the wire. I'll just call this R. It's really R of the wire, RW. Then you're going to have parasitic capacitance that you don't like across there. And this is a correct model for an inductor's impedance at high frequency. Now I got to tell you this. When you look at this, I'll just tell you, the impedance of this is going to be 1 over SC, and the impedance of this is SL, where S is J omega. That's the way it goes. So if you just look at this and don't do any more except go through a thought process to see what it should look like. At very low frequencies, it's just going to look like a resistor, because S is 0. You all follow me? All right, as you get higher and higher frequencies, the first thing that actually turns on is that circuit. All of a sudden, this inductive reactance is going to be greater than this resistance. And the point that it kicks in at is when SL is equal to this in magnitude R. That's your first break frequency. So when you're plotting the impedance in a Bode plot form, if you put versus frequency, really it's the log of the frequency here, and you put 20 times the log of Z here, you start off with the value of resistance, just resistance there. Then, this frequency right here, I call it F low right here, is when R is equal to SL, or really L is equal to R over S. And if you put it in terms of frequency, it's just going to be the resistance of the wire over, and you can put omega, well, I have F, so it's going to be 2 pi F, and it's going to be times, this is going to be F low right here, and this would be the value of the inductance. And if you want to know what FL is, you can say, if you want to know that, you simply take it over here and you can say F low is going to be equal to R over 2 pi times L. So this is and then it's going to start going up at plus 20 dB per decade. until it hits the self-resonance frequency here. And the self-resonance will be 1 over square root of LC. And of course, that's the parasitic capacitance. After it hits self-resonance, it's going to come down at minus 20 dB per decade. And that's the way an inductor looks, period. Now, based on that plot that he had, now this is the typical model that's used. I think that problem's messed up. This is a plot that will get that, guaranteed. It'll give you that. And in Dr. Lutmer's book, does he show you, I'm trying to find out, if he hasn't plotted the inductive impedance in it. No, I don't see one. Guaranteed that's what they look like. That plot will go with that circuit for a boat.
I found it.
What page?
Bottom of page 511.
Okay. That's the circuit, but not the plot.
Oh.
On 511, yeah, that's the circuit, but he doesn't, you know, in the book, like in EMC books, electromagnetic compatibility books, they'll have the plot shown in the Bode plot for both the capacitor, the resistor, and the inductor, what they look like, okay? Now, I'm glad I got that done. That will give you this guaranteed. If you do it on MATLAB, you'll see it. After that, the next thing we have to talk about wires and what they look like in high frequencies. And we've already talked about skin depth, right? In here? Yes. All right, so now what we do is talk about what the wires AC and DC resistance look like, and then in inductors, AC and DC internal inductance. So the first thing is when we have a wire, this is just a wire, it's going to have a given radius A, it's going to have some length L, and maybe I should use small l here. As you think about it, if you attached a battery here, and you drove current this way, be a voltage here. This is the standard problem you did in EMAG 1, right? It's a constant cross-sectional area, long rod, that's all it is. If you take a look at this, the way you calculate the resistance, first you assumed I, right? You're assuming you know this. Then after that, you're going to say it's equally distributed over this cross-sectional area. So you get J, and you say J is nothing more than I over pi a squared if it's a circular wire. And you can say it's in the AZ direction, but that's not really important. Y'all follow me? You remember the next step? After you get J, what do you do? I taught some of you. E, right? So J is equal to sigma E, right? So now I get E. So my value of E is J over sigma. And now I see it's I over pi a squared times sigma. Y'all follow me? Once you have E, we need the voltage, so we integrate to get the voltage. We simply integrate from 0 to L over the length, 0 to L, E dot dl. Well, E's magnitude, this would be in the AZ direction, if I call this axis C. It's constant value, so I'm really just taking the value of E and multiplying it by the length. So then I say this is going to be equal to nothing more than this, I over pi a squared divided by sigma times L, the length, and that is going to be the voltage. Well, here's my voltage right here. That's where I started with I, assumed I, and ended up with V in terms of the actual value of I and the geometric parameters. So then I get the resistance, and this is the DC resistance, and that's equal to simply V over I, and you can just take a look at that. That's equal to L over pi a squared of the cross-sectional area of that wire divided by sigma, and that would be in ohms. If you wanted the resistance per unit length, you just get rid of L. Y'all remember that? That's just standard DC resistance. For AC resistance, there's one thing that changes. Now, instead of assuming that that current is uniformly distributed over the surface of the wire, we say it's really all gonna flow just over something one skin depth deep. So this is gonna be the condition for this now, it's RDC. This is gonna be R high frequency or AC, and this is when the skin depth is less than A. You might as well put much less than A, because that's the way it usually ends up being. To get this, resistance, remember up here what we actually found is AC, for the DC resistance, that's proportional to length, inversely proportional to sigma, and inversely proportional to the cross-sectional area. Y'all follow me? Alright, now when we get the high frequency resistance, the only thing that happens is the cross-sectional area changes. It still has the same length. The value of sigma would be for the material used, for copper, whatever, but now the area, and I think I told you how to do this, right? You just break that thing and, lay it out flat, like this. It's a skin depth thick, and the length of it is gonna be the perimeter at 2 pi A. Y'all follow me? Didn't I do this in this class? Remember me doing? Sure. So then this becomes simply 2 pi A times the skin depth, and that would be the resistance AC. And that can be much, much greater than the DC resistance. At very high frequencies, it tends to be almost infinite when the skin depth goes to 0. That's the resistance. Y'all, just get that down. That's how a wire looks at high frequency when all of a sudden skin depth takes over. Now when we talk about inductance, I don't have time to do this whole calculation, but when you talk about the inductance of a wire, remember how you calculated the internal inductance back in the day? Anybody? Want to tell me? How many remember the term internal inductance, at least, that term? Surely you do. Internal inductance, the way you would do it is assume a current, right? Then you get J, and after you get J, you have to find the magnetic field at any given radial distance. Once you have the magnetic field, you say the magnetic energy density is 1/2 mu h squared, right? Then you have to integrate that over the volume of the wire and set that equal to 1/2 Li squared. How many vaguely remember doing something like that? If you're in my class, you did it. All right. It gives you one result that's very important. Now write this down. So, this is the internal inductance of wire, and this is the big thing. And I'll do this per meter. This is going to be per meter. It's simply equal to mu over 8 pi, and that's henries per meter. What's the one thing that should astonish you, or at least seems to? It's not a function of radius. It doesn't matter if the radius is 1 meter or 1 micron. That's the internal inductance, and that's a unique feature of this. But this is the DC. So make sure you put that down. DC internal inductance. Okay. The AC internal inductance, and I'm not going to prove this, frankly, because right now I don't think I'm going to have time to. But so what you have to do is you have to go ahead and say all the currents limited to the skin depth. Then you have to calculate the H field. From the H field, you get 1/2 mu H squared. Then you have to integrate that thing, set it equal 1/2 Li squared. At the end of the day, what happens is it's the same thing. You start with the DC inductance from mu over 8 pi, and then you multiply it by 2 times the skin depth, and then it's over the radius of the wire. Matter of fact, I use the term RW here. RW is wire radius. And this is skin depth, or 1 over the square root of pi f mu sigma. Now where this calculation becomes of importance is when the skin depth is much less than the radius of the wire. It could be of the order of the radius of the wire, but then this will be the actual internal inductance. And he has some of this information. Hold on for 1 second. I'll tell you where he has it. Well, he has it on, equation 9.6 on 505, but what he does, it's not per meter, so he multiplies by L, and he doesn't break out the mu over 8 pi, he just puts mu over 4 pi, and then he has, skin depth over A. Are you with me, class? So that, and by the way, that's the internal inductance. Now, the next thing you have to be aware of, internal inductance may or may not be important, because the dominant inductance usually has to do with magnetic energy outside that wire. That's usually the thing that limits everything. So now you have to talk about the return path for current. And this is important that you appreciate this. Now, let me do it this way. If you take a look at just a two-wire pair, if I have I this way, and these are always driven in differential mode, and I have I this way. Right? The closer these two wires get to each other, the less the magnetic energy in the surrounding area. As a matter of fact, when I overlaps this one, there is no magnetic energy. Do y'all follow me, class? Because then there's no current, technically. But the external energy that you have, magnetic energy, has to do with the separation distance of these wires. And if I come down, if I just take a wire there and a wire here, there's a huge area where you can have an H field that's significant between those two things. It'll have a tremendous amount of magnetic energy. So the return path, the way the current actually returns to its source becomes critical. And there's a lot of information we can talk about here. But the way they deal with this, it's sort of a catch-all way, and it's an approximation. They say the entire external inductance for a wire can be approximated by what's called a partial inductance formula. And this is on page 505. So when I'm talking about partial induction, it's an estimate of the external inductance. If we knew the exact return path for the current, we could get it. But a lot of times you don't, and that's just a fact of life. You know you got a wire going down there, and you got some current coming back here through another wire, but you really don't know the exact path of the current case. You can estimate it, but that's about as good as it gets. So this is a partial inductance, and this is equation 9.7. I want to say one thing about this equation. The way they did this was estimate the near field energy in a wire. And there's a lot of things on this that get kind of hairy, but so they say L can be approximate. This is external inductance. L external can be approximated as, and he uses this form, 10 to the minus 7, and then it's going to be times L, the length of the wire, and then it's going to be times the natural log of 2L over the radius of the wire minus 1. Doesn't look like it came from anything. It was actually developed to approximate the value, and this would be in henries. And here L is the simple length of the wire, and it should be in meters, by the way. And the RW is the radius of the wire. Now, I want to tell you one thing. How accurate this thing is, I'm not absolutely certain. I know it's been developed and used by a lot of people in the real world when they're trying to estimate the external inductance of wires where they don't know the entire return path. But it is used, so I'll just leave it there. He says that in his book, he has this. The formula is based on partial inductance, a concept, a subject which is beyond the scope of this text. Basically, he doesn't want to mess with it. But it's fair to say that probably my EMC class is going to see this. Oh, there you go. Yeah, you're going to see that in EMC, but I'm not going to go through the proof here. So then the next thing we talk about is the fact that I'm out of time. And that's an unfortunate reality. I get that problem. I'll get you the right answers to that, but that's an odd kind of thing for him to mess up. He's usually very good. I'll make sure it's right. And, come back Monday and the test is on Friday. So you're gonna get some homework, not much, but I know it's fall break, I didn't give anything on the break. I need you at least to stay up to speed on this wire business. That's the problem that bothers me. Because wait, was that the right spot for that, Phil? Are we good? Oh. Thank you. Is this everything? Yeah, I don't think
I have a stapler right here, that makes it easier.
Do you offer the same class in spring?
No, I do radar this spring. But let me just go through that part. I wanna do it. Wanna hang around?
I think I gotta head on today, I gotta go home this
Oh,
afternoon.
you want to? Well, I'm gonna do it here. But I wanna pull that thing out. Something doesn't look right.
I played around with it, or I don't know, if you leave out the 2 pi factor, it comes out to 10 megahertz. Off by just a factor of 10.
No, there's.
Was the 100 ohms, originally, was it in DC instead of,
Well, tell you what, hang on one second. Let me just pull that.
I have no idea, I'm just, it was off, like, I was playing around with the numbers, and if you leave out the 2 pi in the ending calculation, you get 10 megahertz. And if you convert it to 100, that could be, have a good weekend, I don't know.
All right, you two, take care.
I don't know. Whose laptop is that? Is this laptop in here?
No, that's the fella that records.
Did he leave his laptop in there?
He may be coming back for it.
Oh, man.
out of that problem.
This is the actual value. For whatever reason, remember this was like 100 kilohertz, and this is 1 megahertz. That's wrong. This is the values.
Huh.
This is
Your graph was right.
Now this is wrong. This problem is not to do with this. Up here. This is the problem. There's the graph. You should.
So you put it in the wrong spot.
I don't know how that happened. I'm actually trying to figure it out. Oh, I see how.
It's on another page.
This is on page 375. That's the one I'm looking at. And somehow I got that in there. There it is.
Hey, JD. I was about to say, I was really, I would, I mean, oh, I gotcha. Oh, yeah, it's still here. Can I just hit stop on the recording and it's fine?